This video will give an overview of hypothesis testing for one population mean. This will cover the beginning of Chapter 9, sections 9.1 through 9.3. So what exactly is a hypothesis test? Let's look at a little scenario first before we begin. Prior to this past semester, RVCC students spent approximately 6 hours per week outside of class time on a 3-credit class. So this data was obtained probably through some sort of student success survey, various information. It's some fact that is just known to be true, that students spend approximately 6 hours per week, 2 hours for every 1 hour in a classroom. Now, the college administration has concerns that this has changed during the spring 2020 semester due to COVID-19. So, to substantiate their claim, 30 randomly selected students were asked how much time have they spent on their 3-credit class for the second half of spring 2020. And the average amount came out to 5.3 hours. Now, problem is this enough to say, hey, students are now, we took this sample of 30 students and students are now spending less time and we're done. That's not the case. Because it is a sample of only 30 students, we need to know if that sample itself provided sufficient evidence for us to now make the claim that students are no longer spending 6 hours on their coursework. And this is where a hypothesis test comes in. It helps us to determine if that particular sample of 30 students provided us with sufficient evidence. To conduct a hypothesis test, there's a lot of information going on here in this particular problem. We have to start with what we call that null hypothesis. What is the known fact that we're trying to test? That known fact is the 6 hours. What are we testing? Are we saying, is the administration coming in and saying it's now more than 6 hours? It's now not equal, different from 6 hours, or do they feel it's less than 6 hours? So basically, even though our amount came out less at 5.3, the administration has concerns that it is simply changed. So when you go to complete that alternative hypothesis, it's just a general statement in relation to the original one of equal to, not equal to 6, less than 6, greater than 6. So again, a lot of information is going on here. We're going to take a look at the kind of theories behind this hypothesis test, understand the terms and the vocabulary, and then in the next video, we'll actually work out some problems. So again, let's go back to this idea of the null and alternative. Your null hypothesis is that hypothesis that is to be tested. In this particular problem that I put up there, our null hypothesis, which is designated as H sub 0, is simply equal to 6, because that is what we believed to be true. The alternative is what we now think is happening. Now, when the alternative hypothesis is set, there's a couple different options. Alternative hypothesis can simply be not equal to 6, as it would be in this case, because the administration just wants to see if it has changed. Or, if the problem had read, the administration believes that it's decreased, we could go ahead and write an alternative of less than 6. Or if the administration came out and says, well, students aren't leaving their house, we believe it's now increased, we would write our alternative as greater than, but the original would always be the same. Every problem you're going to do is going to be different, but every problem is going to very clearly fall into one of these categories. And the keywords you're looking for are less than, greater than, different, changed, and it'll let you know which of those categories your alternative is going to fall into. One thing I want to make it clear though, your null and your alternative always use what we call the population mean mu. In hypothesis testing, mu sub O in this particular problem is our 6. Mu sub O represents that population mean we believe to be true that we're trying to test against. Okay? The hypothesis test itself is a number of steps that we're going to do, and then eventually we're going to be able to come to a conclusion to determine if that null hypothesis should be rejected in favor of the alternative or not rejected and kept. If your null hypothesis is rejected, that means we are concluding that our sample data did provide sufficient evidence to support the alternative. If our null hypothesis is not rejected, then we are concluding that the data did not provide sufficient evidence to support the alternative. These are all conducted at specific significance levels. A significance level is something that is given to you in the problem. We use alpha to represent the symbol for our significance, and it is commonly 0.05. Sometimes it is high as 0.10, and sometimes it is low as 0.01. These are common significance levels, and we will talk about them throughout the video. Now, when using a sample, there is always a chance of making some sort of error. And I'm not talking about a mathematical or a calculation error here. These are sampling errors because there is that chance, even if you do a random sample, there is the possibility that you could end up collecting all data that happens to be on the high end or all data that happens to be on the low end of your sample. We could have ended up collecting in our particular sample all the data of students who do work at least 6 or even more. Or we could have ended up collecting data from a bunch of students who only put in 4 hours. So these are the errors that are going to occur. Your type 1 error is when you end up rejecting the null hypothesis because your hypothesis test showed that there is sufficient evidence in your sample, but in reality, that null hypothesis was indeed true. This error is set by the researcher who's conducting the hypothesis test. For your problems that you're going to do, it's going to be given to you and it's your alpha level. So you'll go into a problem saying, okay, I'm going to allow an alpha of 0.05. I'm going to allow a 5% chance of making a type 1 error. Okay? Type 2 errors are the opposite. Type 2 errors occur when your sample doesn't give you enough evidence, so you don't end up rejecting, but in reality, this null hypothesis is indeed false and it should have been rejected. This particular error is known as a capital Greek letter B, beta, and this is something that we're going to work on at the end of this particular chapter, how we calculate beta. So again, the probability of making a type 1 error is that significance level. It is your alpha. you're going to use it in every single problem you work on. Beta is something we'll get to at the end of the chapter. Is there a relationship? They are not complementary in that you cannot just add them up and they equal 1. One is not 1 minus the other, but it is true that for a fixed sample size, the smaller you specify your significance level, because everyone might say, well, why don't we do every hypothesis test at the lowest possible significance level, giving us the lowest chance of making a type 1 error? What happens at that point is you create a larger probability of making a type 2 error. So they do have that bit of relationship. So our general steps. In your Canvas course, I also have these detailed for you as well, but your general basic steps without any, and we will go through these steps regularly. Number 1, you always have to state your HO and your HA. If you're in the Stat 1 course, we're only going to be working with one population mean, so your HOs are always going to be mu equals, mu is greater than, less than, or not equal to for HA. But in Stat 2, these hypotheses become a bit more complicated. We're going to be pulling in 2 populations. We're going to look at different types of parameters besides a mean. We're going to be looking at proportions. We're also going to be doing different types of tests with multiple populations, and your null and your alternative hypothesis are actually sentences you're going to write. So this as you move into Stat 2 can become much more complicated. Step 2 this is where I call, just read the problem and jot down the correct information. So state significance level equals, state what your sample mean is, your sample size, your standard deviation. Sometimes we will be using sample standard deviations. Sometimes we will be using population standard deviations. You've got to get used to using the correct terminology. And this step 2 is where you can list all the valuable information that you are then going to take to step 3, which is where the calculations take place. And this is what we'll look at in the next video, is these specific formulas for calculating test statistics. Now, step 4 and 5, you will not be doing, Step 4, you will be doing one of these 2 approaches. You have to know how to do both the critical value and the p-value approach. We're going to talk about them in this video in a little more detail. And I will make sure we go through examples in the next video for each. When it comes time for the test, sometimes I will specify, I want you to use this approach. Other times I will allow you to choose the approach. Either way, you have to show all the work for the approach. Step 5, that's just your conclusion. After you do your critical value or p-value approach, you're going to be able to come out and say, I reject or do not reject the null hypothesis. And then your last step is to interpret. This is a sentence you're going to write in relation to the context of the original problem. So a sample, if that original problem I gave you, we ended up rejecting, we're not going to do it, that wasn't real data. But if we did end up rejecting, your interpretation might look something like this. At that 5% significance level, the data do provide sufficient evidence to conclude that RVCC students are no longer spending 6 hours on coursework, because we're rejecting that null hypothesis that they are spending 6 hours. Now, what does a do not reject interpretation look like? At that 5% significance level, the data do not provide sufficient evidence to conclude that RVCC students are spending a different amount of time, because we're not rejecting. So this just gives you a nice little overview of those steps that we will go into much more detail. What I'd like to do is spend a little bit of time understanding those 2 approaches before we use them in a problem. So section 9.2 looks at what we call the critical value approach. Students like the critical value approach. It's visual, it's kind of easy to set up. It takes our normal curve that you're used to working with by now and separates it into a rejection region and a do not reject region. And the critical values themselves are what separates them, the rejection from the do not reject region. So let's take a look at what I mean by this. Keep in mind, we have 3 different types of tests depending on that alternative hypothesis. So if your alternative hypothesis was mu does not equal, I'm going to go with the 6 from what we were using before, we have what we call a two-tailed test. I'll put it over here. Now, if you had an alternative hypothesis that said mu is less than that known mean, then you have what's called a left-tailed test. And if you have an alternative that says mu is greater than, you are going to end up with a right-tailed test. And this is very standard. Anytime you have not equal to, it's two-tailed. Anytime you have less than, it's left-tailed. And anytime you have greater than, it is right-tailed. So how you set up, and again, this is all determined by the wording of the problem itself. You then draw a picture. And what we need to do is we get these rejection regions. So the tails are the rejection regions. If it's left-tailed, we have 1 rejection region. If it's right-tailed, we have 1, it's to the right. And if it's two-tailed, we have 2 rejection regions. So where do we get these rejection regions from and what determines them? That's what our critical value is. Okay, we need to get our critical value. Our critical value comes directly from that significance level, alpha. Okay, so now let's talk about what gets us those rejection and do not reject regions. And let's do it. Let's suppose we were doing a problem with a 0.05 significance level. Take a look at the pictures. We're going to look at the left-tailed and right-tailed first. The 0.05 is the area that occurs in the rejection region for that significance level. So that means for a left-tailed test, this area right here will be 0.05. For a right-tailed test, it too will be 0.05. But for a two-tailed test, that 0.05 must be separated into the 2 tails. That's why it's listed as alpha over 2. And then we have on each side 0.025, so that together they make up 0.05. The rejection region area to do a critical value test becomes the same as your significance level. Okay? So all we need to do, kind of like we did with confidence intervals, is figure out what is negative z. Sorry, that is definitely not a z. Negative z of 0.025 and z of 0.025. Well, if you recall, at the bottom of your t-table, there was that little shortcut with common z-scores, and 0.025 is 1.96 and negative 1.96. So that means this area here is negative 1.9. This area, this number on the number line is negative 1.96, and this one is 1.96. But for the left-tailed and right-tailed, we need z, negative and positive, z of 0.05, and that's going to be 1.645. And negative. So again, you're only doing one of these pictures because your problem is only going to have either a not equal to, a less than, or a greater than. You're not doing all three at once. This gets you your critical value. At some point, you are going to calculate a test statistic. Your test statistics tend to fall between -3 and 3, but sometimes they can be a bit more extreme. So if your test statistic, for example, I am completely making this up, was 1 point, or let's say it was 2.1. If our test statistic for a right-tailed test was 2.1, if 1.645 is here, our test statistic would fall then in what we would call the rejection region. Okay? But if, again, for a right-tailed test, our test statistic was only 1.3, then it would fall here, and it would be in the do not reject region. So again, a lot of this will depend on whether you're doing a two-tailed, left-tailed, right-tailed, and what your test statistic's going to be, what your significance level is, and that will determine whether you end up rejecting or not rejecting. But the key point here is the critical value approach uses numbers along the number line to determine rejection. The critical value is kind of the cutoff point for the reject and do not reject, and your test statistic will fall somewhere on this number line. If it falls in the reject region, you reject. If it falls in do not reject, you do not reject. Now, P-value approach does the opposite. P-value approach uses the areas under the curve. P-value approach is the approach that is most commonly done in real life research, because a p-value is what it sounds like. It's a probability. It is the probability of getting the sample results you got if the null hypothesis were indeed true. Okay, so basically in that problem we started out with, remember our sample showed 5.3. We were comparing it against the 6. And we would have to do a whole bunch of work to get a test statistic, turn our test statistic into a p-value. A p-value is a probability. P-values can only be between 0 and 1. If you're getting a p-value that's not between 0 and 1, you're probably doing a critical value. So you need to differentiate between the two. P-values do not come from the significance level like the critical value does. It comes from the actual test statistic that we're going to calculate in the next video. And again, it's a probability. It's the probability if this were indeed true. You know, if the null hypothesis were true, what's the chance of us actually pulling a sample as low as 5.3? If the chance of that occurring is so small, then we could say, you know what? Our sample provides enough evidence to say this is probably no longer true. But if our probability is pretty high of pulling a sample of 5.3, if our actual sample is a 6, then we can't reject it. So the question becomes, what constitutes small and not small when we're determining a p-value? Is 20.20 small enough? Is 0.10 small enough? Is 0.05 small enough? So to help us determine that, what we do when we get our p-value is we simply compare it to alpha. So remember, you are always given an alpha in a problem. you will be able to either get a p-value or at least a range for a p-value. So let's suppose our p-value came out to 0.043. So the probability of getting the results we got is 0.043 or 4.3%, but our significance level was 5%. So the question is, how do you compare p to alpha? In this case, 0.043 is indeed smaller than 0.05. And anytime p is less than alpha, you reject. If p is not less than or equal to alpha, you do not reject. We will be spending a lot more time, and I think these will become a lot easier for you to see as we go through some problems. But here's what I want you to notice. The picture changes when we do the p-value approach. Number one, these values here are your test statistic. They are no longer those alpha levels. All right, so this is a formula. You're going to calculate a test statistic. It's going to go along the number line. The area represents the area from the test statistic. So let's do a quick example. We're going to use the right-tailed approach. Let's suppose we do a problem and we get a test statistic of 2.3. So that means that you're going to be drawing lots of pictures when you're going through hypothesis tests. So let's suppose we're doing a right-tailed test and my test stat is 2.3. You have already learned how to find an area. This area is your p-value. So you go to your table. Sorry, I don't know why I wrote that as a t. Can you change that to a z? We're going to use a z value. So your z test statistic is 2.3. I was doing t for test stat, but that will end up being confusing. So your z test statistic is 2.3. What I want you to do is go to your classic z table, look down the z, find 2.3 on your z table, and when you find 2.3 on your z table, it gives you an area of 0.9893. But that is the area to the left, 0.9893. So you are going to have to subtract that from 1 to get the area on the other side. So 1 minus 0.9893 equals 0.0107. This side is 0.0107. That is your p-value. So you get p-values by finding areas under a curve at specific test statistics, which are z-scores. Sometimes they're z-scores, sometimes they're going to be t-scores. We're going to do examples of each. Okay. So let's take a look at one more. Let's suppose we got a z test statistic of negative 1.199. We're doing a left-tailed test. So I can look up negative 1.19 on my z table. Hit pause and look it up yourself. Negative 1.19 appears to be 0.11. 0.117. Oh, remember your table always gives you the area to left. In this particular problem, we do not have to subtract from 0. Because it's a left-tailed test, we want the area to the left. And this is why drawing pictures becomes so important, because if you draw the picture, you never have to ask yourself, do I have to subtract from 1 or don't I have to subtract from 1? So in this case, my p-value would be 0.1170. Since significance levels are usually numbers like 0.10, 0.05, 0.01, this would be a kind of a high p-value, and this would end up being a do not reject. We are using significance levels for this course to determine whether to reject or not reject, but in reality, sometimes p-values are just stated, and how small they are really kind of depends on, I'm going to skip for a second to here. Obviously, anything less than 0.01 is considered very strong evidence. Anything less than 0.05 is still considered strong. You get into a moderate area between 0.05 and 0.10, keeping in mind if alpha equaled 0.10, you would still reject because your p-value would be less than alpha. Anything above 0.10, though, pretty much it never gets rejected. That is considered either weak evidence or no evidence at all. You don't need to know this. All you really need to do is test your p-value against alpha. But in reality, whether a researcher rejects or doesn't reject, they tend to use a chart like this. These steps look like my other 6 steps. They're just very similar to the Pvalue approach. We'll go over these in detail when we do a problem. So again, this is just a brief overview. Not very brief, I guess, because it was 30 minutes, but this is just an overview video. In the next video, we're actually going to be working out some problems.